Every second, millions of automated decisions run our modern world, categorizing data, routing logistics, and driving trades faster than human comprehension. But the vast majority of these systems rely on what statisticians call a point prediction, a single, rigid numerical output, like a demand forecast of exact 100 units. For real risk assessment, a solitary number provides no useful context. It tells you nothing about the plausible range of alternative outcomes if conditions shift. If a supply chain manager orders inventory based on a rigid forecast of 100 units, they are blind to the fact that actual demand might safely swing to 50, creating costly overstock, or spike to 150, triggering massive shortages. Similar cascading errors occur when a trading algorithm misprices a volatile asset, or when a medical diagnostic model delivers a binary result without accounting for biological variance. Point predictions identify the most likely path, but in high-stakes environments, that path is incomplete without the precise boundaries of potential failure. To solve this, data scientists typically look at the model's internal confidence scores, relying on built-in probability functions to gauge certainty. The flaw in this approach is a pervasive mathematical problem known as miscalibration. This usually manifests as overconfident miscalibration, where a model fails to capture the true, real-world outcome. Conversely, underconfident miscalibration produces excessively wide intervals. While these might capture the truth, they are practically useless for any precise decision-making. A system might claim a 95% confidence interval, but against live data, actual observations frequently fall outside those bounds. Traditional techniques like Bayesian inference or ensemble variance lack rigorous finite sample guarantees. Their math only works on infinite data or perfect theoretical conditions. The result is performative uncertainty. It looks like rigorous risk management on a dashboard, but it collapses the moment it encounters the friction of deployment. Standard machine learning confidence scores are ultimately measuring a model's internal mathematical state, not its actual reliability when confronting unseen data. Before engineers can guarantee the reliability of a model, they first need a way to accurately measure its probabilistic accuracy. This is done using proper scoring rules, mathematical tools designed to evaluate the quality of an entire predicted probability distribution, rather than judging a single point prediction. A proper scoring rule forces a model to truthfully report its actual uncertainty. It heavily penalizes algorithms that output unearned overconfidence or lazy underconfidence. In continuous regression tasks, the premier metric for this evaluation is the Continuous Ranked Probability Score, or CRPS. This chart shows the visual representation of CRPS, plotting cumulative probability on the vertical axis against the specific forecast values along the bottom. That smooth red curve represents the model's predicted cumulative distribution, its complete probabilistic forecast across all possible values. The sharp vertical dashed blue line represents the step function of the true observed value, what actually happened in reality. The gap between the forecast and the reality creates this orange shaded area. This area represents the integrated square difference. It is the exact mathematical penalty the model pays for being uncalibrated or lacking sharpness. CRPS effectively takes the concept of mean absolute error and expands it to evaluate full distributions, forcing models to be completely honest about their exact spread of uncertainty. Yet, CRPS and all other proper scoring rules share one fatal limitation. They are purely retrospective diagnostics. These metrics can only confirm how well a model captured the uncertainty on past, already observed data. Achieving an outstanding historical CRPS score does not mathematically ensure that the model's prediction intervals will actually hold true for tomorrow's inputs. High-stakes deployment environments cannot survive on historical reviews alone. They demand proactive certainty. Knowing a system performed well in testing is insufficient. Engineers need a concrete mechanism that explicitly guarantees future coverage. Data scientists address this gap between internal model scores and real-world reliability through a framework known as conformal prediction. Conformal prediction is not a new model architecture. It is a statistically rigorous, entirely model-agnostic wrapper. Its defining advantage is that practitioners do not need to abandon or retrain their existing models, whether they are running a simple linear regression or a massive deep learning network. Raw data enters the black box base model, which outputs its typical rigid point prediction. That prediction then passes through the conformal wrapper, which instantly translates it into a dynamic, flexible boundary. Conformal prediction bridges the gap between complex artificial intelligence and reliable statistics, transforming any rigid predictor into a fully calibrated probabilistic system. For this wrapper to function, it requires a held-out calibration dataset and one core mathematical assumption: exchangeability. Exchangeability simply assumes that future, unseen data will behave symmetrically to the past calibration data. Unlike traditional statistics, conformal prediction provides finite sample guarantees. It does not require infinite data or perfectly normal distributions to remain mathematically valid. In a regression task, the output is a specific prediction interval, dynamically sized to ensure it captures the true numerical value at the exact confidence level specified by the user. In a classification task, it outputs a set of possible labels, like benign or malignant, guaranteed to contain the true label at that exact same specified confidence level. Conformal prediction entirely replaces vague algorithmic guesses with explicit, mathematically verifiable guarantees. To see the operational impact of this framework, we can observe conformal prediction actively deployed in a high-stakes environment. We can set up a direct comparison: an uncalibrated model on the left and a conformal wrapper on the right, both reacting to the identical turbulent stream of live data. On the uncalibrated side, the static, narrow band stays rigid. As conditions fluctuate, nearly 30% of the incoming data points fall completely outside its established bounds. On the conformal side, the confidence band dynamically expands and contracts with the shifting variance of the data, successfully capturing exactly 95% of the incoming points. The conformal layer acts as an automatic regulator. It expands the interval when the base model is too confident, and tightens it when the model is underconfident. This forces the system's reported confidence to perfectly align with empirical reality, completely eliminating dangerous operational blind spots. The original stakes for these systems remain immense, governing global supply chains, algorithmic trading floors, and automated medical interventions. True risk management in these fields demands an honest, rigorous ledger of uncertainty, not aspirational marketing output from an AI vendor. A trustworthy system automatically adjusts to external stress, maintaining strict control over volatile inputs. Conformal prediction solves this performative uncertainty problem by delivering a distribution-free, model-agnostic truth mechanism. That 95% confidence level is backed by a finite sample guarantee that remains valid even as the underlying data distribution shifts.